This video is all about the product rule, where we are differentiating a situation where we've got one function multiplied by another function. So let me show you a few examples of what that might look like, so you know when we're going to be using the product rule. In every one of these questions, we would use the product rule, because in the first situation, I've got the x multiplied by the 2x minus 1 cubed. In the second situation, we've got the 3x to the power 4 multiplied by the e to the 2x plus 3. Here we've got the x multiplied by the square root of x minus 1. Here we've got the x squared times the ln of x plus 6. Here we've got the x times the 1 minus 5x to the power 4. Here we've got the x plus 2 times the x minus 3 cubed. Here we've got the x to the power 4 over 3 multiplied by the e to the 3x. Here we have the x plus 1 times the ln x squared minus 1. And here we've got the x squared multiplied by the square root of 3x plus 1. In all of these examples, we would use the product rule, which looks like this. And I will post a link in the description to this video of the proof of this formula. But basically, we differentiate the f function to get f dash, and we multiply it by the g function. Then we differentiate the g function, and we times that by the f function, and then we add the results together. Like I say, I will post a link in the description to this video of the proof of that formula using our good old friend differentiation from first principles. You don't need to know the proof, you just need to be able to use it. I don't particularly like that notation. I think that notation is quite long, so instead the notation I prefer is this shorter notation, where I have u as one function, v as the other function. Notice the weird way I do my v's there. That's so I don't get them mixed up with the u's. When I was your age, I used to do my u's like that and my v's like that, and then I quite often got myself mixed up and made mistakes with my maths. So hence why I now very clearly do my u's like this and my v's like that, so I don't get confused. Anyway, we differentiate the u function, times it by the v function, and then we do the opposite. We differentiate the v function, times it by the u function, and then add the results together. So that is the product rule. Let's now see a few examples using it. So here we want to differentiate 20x multiplied by the 1 minus x cubed. So I'm going to say this is my u function and this is my v function. So u equals 20x, v equals 1 minus x cubed. U dash, so differentiating the 20x, I'll get 20. V dash, differentiating the 1 minus x cubed. Now we have to be careful about this, because we've got one function inside another function. So we have to use the chain rule. So I'm going to differentiate the cubed first. So that's going to be 3 lots of the inside squared. And then by the chain rule, I have to multiply that by the derivative of the inside. The derivative of 1 minus x is minus 1. So I'm going to multiply that by minus 1. Simplifying, the 3 times the minus 1 is minus 3. Right, let's now apply the product rule. So I will have u dash times v plus the v dash times the u. So we'll have the minus 3 of the 1 minus x squared multiplied by the 20x. The minus 3 times the 20x will be minus 60x. And then the plus minus 60x will actually turn out just to be the minus 60x 1 minus x squared. So that's been differentiated now. And you could leave your answer like that, but that's not going to be particularly useful for following other steps. We can simplify this. And I'll give an example of why we should definitely want to simplify if we can. The way we're going to simplify this is, first of all, I noticed that there's a 1 minus x squared here, and there is a 1 minus x squared within that 1 minus x cubed there. So I'm going to factorise that 1 minus x squared outside, which will leave from the first bracket a 20, and I will still have 1 power of the 1 minus x. So this times this gives the 1 minus x cubed with the 20 at the front. Then from the second term, we've still got the minus 60x there. Then I noticed that I could factorise out the 20 as well. There's a 20 in there, there's a 20 in there. So I'm also going to factorise 20 out. So that will leave just the 1 minus x at the front. So you can have the brackets there. You don't need those brackets anymore because we've taken the 20 out. And then we've got the minus 60x, which will now just become minus 3x. So I've just done 2 stages of factorising there. I factorised this out first, then I factorised the 20 out. You could have done that in one go if you wanted to, but I often find that students, and myself as well, get confused by trying to factorise too much in one go and make small mistakes. That's why I like to do it in stages, just focusing on one little bit at a time. I then noticed that square bracket there, I can simplify that because the minus x minus 3x is minus 4x. And there we go. That is, let me rewrite it over here. That's my final answer for my gradient function. dy by dx is 20. Lots of 1 minus x squared times 1 minus 4x. So not only should we factorise to make things look neater and tidier, but it is going to be much, much, much easier to solve problems with the gradient function when it's in this form. Because let's say I'm looking for stationary points or turning points. We know a stationary point is when the gradient is equal to 0. So if I make the gradient equal to 0, this is now really easy to solve when it's in its simplified form, because I now know that either this bit has to equal 0 or this bit has to equal 0. So either x is 1 or x is equal to 1/4. So now I've got the x coordinates of the stationary points, and if I wanted the y coordinates, I could substitute those values in here and here to get the y coordinates. So when things have been fully factorised, it makes it nice and easy for finding stationary points or just generally using your gradient function. Second example, we're going to differentiate 3x multiplied by 4x minus 1. This is my u function, this is my v function. So I'm going to say u equals 3x, b equals the square root of 4x plus 1. And I know to differentiate the square root, I need to write it as a power of a half. Differentiating the u function, I get 3. Differentiating the v function, I notice I need to use the chain rule for this because I've got one function inside another function. So let's differentiate the outside function first. So we'll times by a half, keeping the inside the same, take 1 away from the power. Now by the chain rule, I have to multiply this by the derivative of the inside. The derivative of 4x plus 1 is 4. Then we notice that this v dash is going to simplify a little bit because a half times 4 is just 2. Right, so let's now apply the chain rule. So we're going to have u dash times v plus v dash times u. So the 2 times the 3x is 6x. And we've got the 4x plus 1 to the power of minus 1/2. So we've differentiated it. This is the gradient function. But again, like before, it's a little bit messy here. And I notice we've got this 4x plus 1 here that looks kind of similar in both of them. However, I'm not going to factorize in this case because of this negative power. This negative power means I need to take a slightly different approach. Because I know that that negative power means that that 4x plus 1 is actually on the denominator. This is the same thing as having this. So now this makes me start to think about common denominators. The denominator here is currently 1. So if I want to get a common denominator, I want to multiply the bottom here by 4x plus 1 to the power of a half. So that I've got a common denominator here and here. If I do that, I need to do the same thing to the numerator. I need to times by 4x plus 1 to the power of a half. And so this first fraction then, we've got 3 lots of the 4x plus 1 to the power of, now when we multiply these together here, we add the powers, power of a half plus power of a half, so that's power of 1. So I could write the 1 there, or I don't really need that power 1. I could just leave it like that. And now I've got my common denominator, so I can actually add those 2 fractions together as a single fraction. Here I've got 12x, the 3 times the 4, plus the 3 times the 1, so that's plus 3, plus the 6x here. And the 12x and the 6x, we can collect up those like terms to be 18x. And there we go. This is my gradient function in its simplest form. And again, once I've made it look like that, it's nice and easy to find stationary points because I can just say 18x plus 3 over 4x plus 1 to the power of a half is equal to 0. Which means that 18x plus 3 is equal to 0, so x would be minus 1/6, and that would be the x coordinate of my stationary point, should I need to find it. So that's how we can simplify our gradient function if we have a power of -1/2. Last example, and I've already shown all my working out here just to make the video a little bit shorter. The question's asked us to find the equation of the tangent to e to the power 2x cos x at the point when x equals 0. So we know that keyword tangent means we're going to differentiate to get our gradient function. We're then going to sub in the value of x to get the gradient. Once we've got the gradient, we're going to do y equals mx plus c. And then we're going to substitute in a coordinate to get what c is. That's our process when we see the word tangent. In this case, in order to differentiate this, we need to use the product rule because I've got e to the power x times cos x. So I've selected my u to be e to the power 2x. I've selected my v to be cos x. When I've differentiated the exponential, I know the exponential differentiates to be the exponential with the inside staying the same. And then I times by 2 because that's the derivative of the 2x. So e to the power 2x differentiates to be 2e to the 2x. Then differentiating cos, I get a minus sign. Applying the product rule, I've got u dash times v plus v dash times u. So this is my gradient function here. Then I just simplified it a little bit because I noticed I've got an e to the power 2x there and an e to the power 2x there, so I could factorise that out. And that left me with the 2 cos x and the minus sin x. So this is my gradient function in its simplest form, and I'm interested in what the gradient is when x is 0. So I substituted 0 in here, here, and here. So e to the power 0 is 1, cos 0 is 1, and then sin 0 is 0. So basically I've got 1 times 2 times 1, which is 2. So the gradient of my tangent is 2. Hence why I've said y equals 2x plus c. I then wanted to substitute the coordinate in. I know the x coordinate is 0. In order to work out the y coordinate, I've just substituted 0 in here and here. That's what I did here. And e to the power 0 is 1, cos 0 is 1. So 1 times 1 is 1, so my y coordinate is 1. Which was telling me my y-intercept is 1. So therefore, the equation of the tangent is y equals 2x plus 1. And there we go, that is the product rule. If y equals u times v, then the gradient is u dash times v plus u times v dash.